So one more topic I'd like to talk about is Newton's third law and how that pertains to motion. And what I really mean here by motion is because up until now, really, most of the time, we're thinking about, when we're talking about things that are moving and we're throwing things or we're dropping things, we're still really treating things like they're point masses, like they take up no space. This topic maybe is better thought about like that things actually take up space, but they have a center of mass. So I'm going to say center of mass motion. In other words, right here I am, and here's my my center of mass. Well, I got a really big head, so maybe my center of mass is a little higher, but my center of mass is around here. If I was a point mass, that's where all my mass would be concentrated. And so there's a difference between me moving my arms and legs around my center of mass. I can be an octopus with many arms. Moving my arms and legs around the center of mass versus the center of mass itself moving. And in order for my center of mass to move, and we'll prove this in a later chapter, there needs to be an external force on me. In order for my center of mass to move, in order for me to move my whole body to a different position, there needs to be an external force on me. That's something we'll prove in a later chapter. But you probably should understand that my center of mass can stay in one place and I can flail my arms and legs, but my center of mass may go nowhere. So think of sitting on really, really slippery ice. Really slippery ice. Let's make it frictionless ice. Whoops, that says center of mass. Frictionless ice. So if I'm on frictionless ice, think about moving your arms and legs. You can flail your arms and legs all you want, but without a purchase on the ice, without a purchase, you know what that means, without getting a grip on the ground, you can't move yourself to a different position. You can't move yourself. You can't move your center of mass. So this is what I mean by Newton's third law and motion, but I'm talking about translating, what's called translating your center of mass or moving your center of mass. The official physics term is translation of center of mass. That's not a third law fact. That's a second law fact. F net equals ma. You have to have a net force to move a mass. And we've really been thinking about point masses that have all their that take up no space. If we're not talking about point masses, we're talking about centers of mass. So really a Newton's second law thing. It's also a momentum conservation issue, which we talk about in a later chapter. That's what I was talking about a later chapter. So anyway, so we gotta understand that. It takes a net force to move your center of mass. Okay, so then the question is now I've already discussed how you might be on ice, on thin ice. No, not thin ice. We're not going to fall through. Slippery ice. How do you move? You can't move your center of mass, right? How do we actually walk? How do we walk, right? Here's a dog that's walking. And what do I mean when I say how do we walk? I mean, how do we move our center of mass forwards, right? So it's his or her center of mass is about there. And how do we move our center of mass forward? And you say, oh, well, my muscles can move my center of mass forward. And that is absolutely incorrect. That is not correct. Your muscles are not moving your center of mass forward. What's moving your center of mass forward? I wish you were here to answer the question because I really want to hear what you have to say. So you really should think about it before you listen to my answer. But what is moving my center of mass forward? Is it my muscles? Oh, well, it's the heart beating. It's sending blood to the muscles. Maybe that's what you mean. No. The heart beating, sending blood to the muscles, eating food, creating energy. The muscles can move all you want, but it doesn't mean that I'm translating my center of mass because, again, put me on a frictionless surface and I can move my legs all day long, but my center of mass ain't going nowhere. What is moving me forwards? What is moving me forwards is the surface that I'm on, is pushing me forwards. So the black vector was meant to be the velocity, but if I want to draw a force, right, the reason why I, or the red dog, moves forwards is because the surface is pushing them forwards. There is no movement without there being friction between the dog and the surface. So the net forward motion comes from friction. But where does that net forward... We haven't quite answered the question. That forward friction comes from the fact that the dog is pushing backwards on the surface. So how do you really move? Stand up and try to move forward. How do you move? You push backwards on the floor, and by Newton's third law, the floor pushes forward on you. So you see that? Right? You're pushing backwards on the floor, and the only reason you can push backwards on the floor is because of the friction between your feet and the floor. So this force here is on the floor, and this force here is on the dog or on you. So the only way you can move is by having an external force push you. That is the only way you can move. And that external force when you're walking is the friction from the floor. So the friction from the floor is actually pushing you forward. And you say, but wait, I thought friction always resisted motion. Yes, but what motion is this friction resisting? This friction is resisting the motion between your feet and the floor. It's resisting your feet from slipping backwards. Right? It's resisting your feet from slipping backwards. So this is still a force of friction which resists the relative motion between two bodies, your feet and the floor. And the fact that you're pushing backwards on the floor means the floor is pushing forwards on you. That's how you move. So let's try to translate to other kinds of motion. Let's take a car. How does a car move? You say the engine. There's an engine. Engine ain't moving the car. What's moving the car? What has to move the car is an external force. What's moving the car? What's moving the car? I think it's pretty obvious now. It's the road, right? The engine is indeed turning the wheels, but think about what direction those wheels are turned in. Those wheels turn, I guess I'd say backwards, right? What those wheels are doing is they are pushing this way on the road. F, wheel on road. So this is not a force on the wheel. This is the force on the road. The wheels are pushing backwards on the road, so they're spinning in a direction so that they're pushing as if the road moved, right? Just like if you're on a gravel road, what happens? The gravel spits out the back. You're pushing the road backwards. So therefore, by Newton's third law, the road therefore pushes forwards on the car. F, road on car. And that is still a frictional force. F, wheel on road. Road. F, wheel on road. F, road on, I guess, wheel. Right? The forward force is actually on the wheel, which is attached to the car's axle, which is attached to the car. So that moves the center of mass of the car forward. Okay. So I hope you're getting it. So now what about an airplane? I don't know why these are all dogs. They're all dogs. Look at that. I didn't mean to make that true. They're all dogs. Okay. I actually prefer rabbits to dogs, but it's not necessarily true. We don't need to argue about that right now. Okay. So how do airplanes move? There is no road, no floor for the airplanes to push on. Right? Remember, in order to move, I'm starting to make this claim that in order to move, you need to push on something which is going to push back on you. And in this case, there is no road, no floor for the airplane to push on. At least once it gets in the air, there isn't. What's the airplane pushing on? The airplane is sucking air in the front and pushing it out the back. Whether it is a prop plane like this one, air is moving that way. The airplane is sucking air through the front and pushing out the back. And if it was a jet plane, it's sucking it into, and I know these are guns, but sucking it into the jet and pushing it out of the jet engine in the back. Air is pushed out the back. So what an airplane does is it pushes the airplane pushes, I don't know exactly how to draw it, the airplane pushes the air in that direction. Not two A's. Airplane on air. And so then what does the air do to the airplane? The air, air on airplane, pushes back on the plane. So the floor is no longer a floor, it is now the air, right? So you always have to push off on something in order to move your center of mass. In this case, it's pushing off the air. The air is being pushed backwards, which in turn, by Newton's third law pair, pushes the air forwards. Okay, so what about a spaceship? A A spaceship, what does it have to push on? In order to move the center of mass, you got to push on something, which will then push back on you. So what does a spaceship push on? It doesn't have a road. It doesn't have a wall. Think about it, by the way. Go up to a wall and push on the wall. What happens? You move in the opposite direction of the wall because the wall is pushing back on you. Okay? So the spaceship doesn't have a road. It doesn't have a wall. You say, well, it has an engine. So doesn't it suck something in the front and send it out the back like an airplane? No. Why not? Because space is a vacuum. There's nothing to suck. So this is what makes space travel so difficult. Because there is nothing in outer space to push on. There isn't. Well, you might say one of the things that they're developing now is a solar sail. And so in that case, you're literally pushing on the photons from the sun, which is pretty cool. Pushing on the photons from the sun, which then push you back. It's not a big force, but they're starting to develop these kinds of solar sails that will push really, really light things, things with very small mass. But that's not how your typical spaceship works. And I think that you know that spaceships actually can propel themselves in outer space. They're not just in free fall. They can propel themselves in outer space. But how do they do it? It's very, very different than the way we propel ourselves on Earth. Because on Earth, every form of propulsion, or nearly every form of propulsion, requires us to push on something. In outer space, there's nothing to push on. So what do? They bring their own wall to push on. What do I mean by that? They have somebody standing at the back of the spaceship, and that person is throwing tennis balls in this direction. And when they throw a tennis ball in that direction, the person who's attached to the spaceship is pushing the tennis ball in that direction, F, person on ball, and therefore the person and the ship feels a force in this direction, F, ball on person. And so therefore what you do is you just bring up a spaceship filled with tennis balls and you throw the tennis balls out the back door and you get the same effect as long as you throw the tennis balls away. You can't keep them because then you have to exert a force to bring them back. And at this point you're saying, what the heck are you talking about with tennis balls? Well, it's not tennis balls. It's things that are tennis ball shaped, just a little smaller, right? They're burning fuel. So in order to propel a spaceship, you've got to have something you can throw out the back door. And in the case of most spaceships, it's going to be burning fuel. So, but the point is that unlike the burning of the fuel in the car, which turns the wheels, which push on the road and the road pushes back, it's the burning fuel itself that you're pushing on, and you're pushing out the back door. And the burning fuel then pushes back on you. And what that means is, in order to propel yourself in outer space, it takes a lot more fuel because that's the thing that you're pushing on. It actually, and this is an issue for space flight, is where you're going to get the fuel. You can't go anywhere if you don't have fuel. Whereas on Earth, if you run out of fuel, you can still go. You don't want to run out of fuel in your airplane. You should probably land if you're lucky. If you run out of fuel in your car, you can still push the car and move it. But if you run out of fuel in your spaceship, you're out of luck. Can't go anywhere. No way to move. And then you start taking the furniture and throwing it out the back door until you start moving in the right direction. And then you can just use your inertia as long as you're pointed at Earth. Throw all the furniture out the back door, point yourself at Earth, and you're going to be okay. Hopefully you get the idea here, though. There's a difference. Spaceflight is very different than other kinds of flight because of this Newton's third law requirement. You got to have something to push on in order to move your center of mass. Well, Newton's third law requirement is that if I push on something, it pushes back on me, and that's how I move. Okie dokie.